Hi audience, this is the second lecture of this lecture series. In this lecture number 2, I'll be discussing the standalone PWM converter and this DC power distribution system. And in the standalone PWM converter, there is one source and one PWM converter and one node. They stand alone. In the past, we were interested in those kind of application, but now our interest in extended to the complicated DC power distribution system connected with many PWM converters in series, parallel, cascaded, and some complicated manner. So the PWM DC power distribution systems are finding the increasing application. So we'll be discussing some features and the natures of this power system. Okay. This is the situation. We have one DC source. DC source can be a standalone DC source like battery cells, fuel cells, okay, stack of them. Usually battery are packed like this in series and in parallel. So there's a stack of standalone voltage sources. Okay, that is the DC. And another thing is, many cases you will be using rectified AC as your substitute for the DC. Okay, that application is called offline power supply. So there are two different types of the DC sources, but there is only one DC source, and there is only one load. Okay, so, but load can be very general things. It can be some equipment, electric equipment, and some electric equipment has many digital logic circuits inside. All right. Sometimes we'll be using resistive load to simplify the discussions, but as I said, that is the purely imaginary things. Nobody will use a simple resistor as a load. Okay, so there is one source and one converter and one node. This type of structure is called standalone DC power converter. In the past, most of application has this form, standalone application. Okay, now they use many converters all together and several different sources, DC sources, AC sources, rectified LC sources, many things. And there are many DC converters connected in series, in parallel, combination of them, or in strange way. Okay, and there are many loads, parallel, or connected in series, cascade, and so on. Okay, so we want to talk about that stuff here. You are only talk about this kind of application, which is very classical. It was very popular in the past, but now it's very limited. But theoretical discussions on this structure is very important to understand the modern power electronics system, which has complicated structure. Okay, so fundamental thing is always very important. Okay, so you have DC source and load, and DC source can be varied. We are assuming this is a constant voltage, but DC source can be changed. For example, the battery will change its out voltage depending on the status of the charging. So maybe the change in the voltage will occur this way, of load drop and linear increase and some sinusoidal variation, something like this. Okay, so load in general, this is another resistor. It requires current. The shape of the current will be varied like this, the increase and drop of lobe tree, and goes like this, and it will change periodically, something like that. This is IO. This is VS. Okay. What you want here is you have a pure DC here, and you hope this works as your ideal voltage source as closely as possible. So theoretically, the out voltage will have some deviation depending on the fluctuation in the input source. This is VO and load current. Okay, but still you have very minimal change with extremely low, very low ripple component, AC component. So ideally, you want to be a pure DC in spite of the variation in the load current and variation in input voltage. Okay, so that is our problem. All right. As I said, two DC sources. DC sources are grouped into two families. One is standalone DC source. The variation occurs in the magnitude of the source voltage, and the rectified AC source will have AC ripple, some noise component. Okay. Usually rectified AC is something like this. This is a rectified version of AC voltage, but you will have some drop here, drop here, drop here. Okay. This occurs when you use bridge rectifier using diode. Okay, because diode is only conducting in this narrow period of this entire period, and it will draw current only this part. So there is just some drop here, right? And the filtered version of this one is it will be like this. This is not a DC. It's something similar to DC, but we consider this is the DC. Rectified AC source becomes a non-ideal DC source, and the switching instant at this point, diode will be turned on and turned off, so there will be some noise. Okay, so you will observe this. So these are non-ideal characteristics of this DC source, and load is not a resistor at all. So it has non-resistive and some impedance characteristics. Okay, this is very important. And digital logic circuits will draw large current when the logic circuits are turned on, and draws zero current when they are turned off. So it absorbs the pulsating current, something similar to this. Okay, so with all these non-ideal characteristics, we want this output voltage as clean as possible, as a pure DC. Okay, that is our requirement. Okay, so this is the standalone DC to DC power conversion, and so functionally speaking, this DC converter consists of two parts, two sub-circuits. One is power stage, and the other one is controller. So power stage is responsible to power conversion. Okay, it will step down the voltage value of this voltage, or step up value of this voltage to the required volt in the load. Okay, and this controller is controlling, generating all the control signal. So this power stage will provide a fixed DC voltage in spite of variation of here and here too. Okay, so power conversion is performed this power stage, and the controller is controlling energy flow control to maintain this voltage to be a constant. Okay, so there are several components you can use in the power stage. MOSFET and the diode are the switching device, semiconductor switching device. So mostly we'll be using MOSFETs, and diode is like the FRD, fast recovery diode, or Schottky diode. Okay, and we'll use energy storage element, inductors and capacitors for filtering the pulse waveforms. So here we have pulse waveforms, and these pulse waveforms will be filtered by the low-pass filter composed of this one and this one. Okay, so we need reactive component, inductors and capacitors, And sometimes we need transformers to increase the level of input and output waveforms without power loss. Okay, without power loss. Right, that is important. We never use the resistive component in power stage because resistor always accompanies with some loss, power loss. Okay, so we try to minimize the resistive component in the power stage, and we never intentionally use resistors. So no resistors will be used here. Right? And controller will be using some ICs for the PWM converter. There are many ICs, PWM chips. And sometimes you will use some discrete component for the, particularly for this voltage feedback compensation. Okay. All right. So here we have some issues to study, to investigate. Okay, so first we'll study power stage component. We'll investigate the basic structure and the characteristic of semiconductor switches. Right, the switches are a little bit different from the device you have seen in the electronics course. These devices are switching all the time at very high frequency. So there is no steady state operation here. So this switching action, with the switching action, the transient period will be repeating forever. Okay, and that also applies to the inductors and the capacitors. They are exposed to periodic voltage and current excitation. Many undergrad students, they think they understand the inductors and the capacitors, and they think their characteristics are easy to understand, but that is not the case in these applications. Right? So they are switching all the time. Okay? So, and also transformer is excited, not a sinusoidal wave, periodic waveform, and this periodically this voltage and current is changing in this manner. Okay? So everything is switching. Then analysis and appreciation of operation of this is not difficult, but you need some different view of circuit component. Okay? So you should have solid understanding about the inductors and the capacitors, okay, in some different perspective from the linear circuit theory. So everything will be switching. That switching action will partly complicate the analysis, and partly it will help or simplify the analysis. Okay? So if you properly understand these basic things, the study of the converter will be much easier. Okay? Without reviewing this basic property of this. Right? So we'll spend some time on this power stage component. Okay? And second is power stage configuration. We have variety of different PWM converter topologies. Okay? And we need this because the requirement of the input voltage and the load current of your application will vary widely. Input voltage will be very small and very large. Okay? Something in between. Same is true for the load current, and sometimes load current will pulsate like this. Okay? So to meet this requirement, we need different topologies for different applications, and also sometimes the ratio between input voltage and output voltage in magnitude will be very small, like 0.5, something like that, very small, and very large, like several hundred. Okay, so and for the most applications, input and output should be isolated electrically, called galvanic isolation for the safety requirement. So if you touch some equipment, DC equipment, if there is no isolation, electrical isolation, if you touch and if the current is leaking, you will be shocked, okay, severely damaged or get killed. So that is a problem. To avoid that situation, there should be the electrical isolation, galvanic isolation, particularly for the home electronics. So power supplies in your home electronics, TVs and computers, everything, there should be isolation in between input and output. That is a requirement. And all these two are static things. That means this property is determined by power stage component or power stage configuration. If you select the component of the power stage and you select one particular circuit topology for your converter, they are fixed. Okay? So this is characteristic of steady state. And there are two other things. One is dynamic modeling and analysis, and the other one is dynamic performance evaluation and control design. Okay? So with this, you can only make the power stage of the converter. To build controller, you need to understand this dynamic modeling and analysis, and to have good closed performance, you should have a good controller. So we only focus on these two topics, and this part will be covered later class. Okay, so this is topic of current class, and this is topic of the later class. But in between, you need some knowledge about the linear system and the control theory. So we have one intermediate course in between regarding the classical and analog control theory. Okay, that is very important. Many people think they need electronics and network theory for the power electronics. But I think the most topic you need to have is this control theory. Okay, so control theory is very important. So the things around you is most of them are feedback controlled system. In fact, okay, so you should understand the basic principle about the feedback control. Then you can apply those knowledges to here, okay, to achieve these goals, right? So, okay, let me give you two examples of modern power electronics system. Okay, this was standalone application, one single source and one single load, and one this converter in between. That was the classical approach, and this is the modern approach. This is the block diagram of power system, DC power distribution system, for example, telecommunication equipment. Okay, so it has this 48 volt, typically the battery pack or fuel cell pack of the fuel cells, and it has output impedance ideally. Okay, not ideally, practically it has the output impedance, and this is the front end converter. Let me talk about this later. Okay, so it has this converter powered from 48 volt and provide 24 volt output. This is called bus or link, DC bus or link, distribution link, and this 24 volt is spread through this, and there are load converter. This is a load. Generally, there are some equipment, something else, inverter or other converters. It can be general load, anything. Okay, so this is called the load converter. Assume they are all converters. Some case they need some inverters, but we assume everything is converter here. So our voltage of them will be maybe 1.4 volt, 0.8 volt, something like this, or 48 volt from 24 volt. Okay. For this structure, we have several load converters, and they are connected in series, and also they are connected in parallel. And this stage and this stage are cascaded, and maybe they have another structure, some strange structure, stacked configuration. Stack means some series connection vertically with some special configuration, right? So this is the simple example. And in front of every converter stage, front-end converter, load converter, there is a filter stage. This is a low-pass filter, LC filter. For simplest case, it looks like this. Simple LC filter like this. Okay. So I'd like to explain why this is required. This is required, right? So if you have converter, you should have a filter stage in front of it. If you have converter, you should have a filter stage. If we connect two converters in this manner, there should be a filter stage, intermediate filter stage. Okay, load of this filter stage is this, is as follows. Suppose this load converter is buck converter. We'll discuss buck converter later very carefully. The input current of this load converter, for the case of buck converter, this looks like this. It's pulsating waveforms. This value is 0, and this value is large values. Okay, so if we decompose this, if you take Fourier transformation, it consists of DC part and AC part. DC part is averaged value of this. So DC part is coming through this direction. Okay, so let's call it IDC. And AC current is coming from the load converter itself. IAC, and this is IDC plus IAC. Okay? So this IAC is circulating like this, right? So load current is absorbing this part, and average value of this current is 0, and only this part is coming here. So this is necessary. Okay, for simple reason, think about the water coming into your house. Okay, the water is coming from the outside of your house, and you are using the water, and the wasted water will go like this. Okay. So you circulate by yourself. You have some filtering equipment, filtering device. So you receive clean water and return the clean water. That is the proper way of using the water. Okay. If you use toilet, the toilet water cannot go through this. Same is true here. Here is this one is pure DC, and then you only take pure DC from this side, and this AC pulsating part of this should circulate through this. Okay, so this load converter absorb this to balance this as a 0. That is the proper way of using this electricity. Okay. Assume you are drawing without this. You are drawing this current directly here. Then in this line there will be some resistive part. it can be small, but there should be a resistor. Then if this type of current is pushing through this, then voltage here will be like this. Because of the voltage drop at the resistor, the DC link voltage will be something like this, which is very bad. Okay, this equipment, this part, we are expecting to receive pure DC like this, but now this type of voltage is coming here. Okay, that will create some problem here. Right, this becomes very important for modern application. All right, and if you use this, only this part is coming in, then this voltage will be dropped by this product of the this, but still that voltage will be constant, something like this. Something like this. Okay, this will be small, but so there is some drop, but this is much desirable than this one. So for this purpose, you should have a filter stage. All right? When you are doing some experiment in your own loop, you can combine two converters together without any problem. That's fine for you. But if you use your converter in this application, you should have proper in this filter stage. This is very important. Okay. Another example. This is block diagram of spacecraft power distribution system. You know what spacecraft is? A satellite. Okay, going around the Earth. Okay. Let me explain the background for this briefly. Maybe this power electronics is very old, very classical. That is not true. Okay? So power electronics start 1960, something like that. Okay? That is directly related the space program. Okay, long time ago, Russia they launched the satellite Sputnik something. Okay? Then the US, they surprised. The Russia is ahead of us in science. Okay? They cannot believe that, or they cannot accept that. So President at that time, JFK, John F. Kennedy, he promised to the US people they'll send men to moon within 10 years. Okay? And they start the space program, and they found out that this power supply in the spacecraft is huge and very heavy because they use the classical approach, resistive solutions. All right. Now that becomes big problem. Okay, because weight in the space is what? It's money. Okay, it requires huge rocket and some fuel like that. So they start looking this part, power supply part. Okay, so power supply is not advancing fast at that time because people think power supply is very simple, nothing to worry about, something like that. That was not true. Okay, so at that time, that power electronics is recognized as engineering. Okay, and so development, advance of the power electronics happened in parallel with advance of this space program. This is the block diagram of power distribution system in the satellite, okay, spacecraft. There are two sources of energy in the spacecraft. One is what? Battery, stack of battery, so battery unit, okay. The other one is this solar array. Solar array unit is receiving the energy from the sun and the generator power, okay. So this one can be very huge, okay. There is some application called International Space Station, ISS. In that applications, this size of this one is like the football field, entire football field. 2 of them, 3 of them, 4 of them, something like that. It's a huge one. And this battery cell is very expensive, and it has very high performance, but still they need this solar array unit and the battery. Okay? And they need many things. This shunt regulator, battery charger, and the battery discharger. Okay? This is the power system. This is the load. This can be some equipment, telescope, some video taking equipment like that. And it requires specific DC voltage, the load current. Okay? They are very expensive things. So it's called payload. They are paying to load this load to this spacecraft. It's called payload. And there are many of them like this. Okay? And this is distribution bus, DC link voltage, DC bus. This should be tightly regulated at fixed voltage. For example, for the space station, you know what space station is. Satellite is going to station and staying there, and people are there, they live there. Okay? And they are coming back through this space shuttle. So, for example, 180 volt DC is distributed throughout this space station, right? And there is another equipment, shunt regulator, and the battery charger, and the battery discharger. Okay? Suppose this, there is a sun. Sun is here, and here is Earth. This is Korean peninsula here, and satellite is something like this. It's orbiting like this, right? This is called the sun-in mode. Sun-in mode, all of energy is coming from the sun. So it has enough energy. It receives enough energy, more than necessary. Okay. For that case, this S1 is S2 is connected in this manner. So the energy is overflowing. So some energy will go like this, and extra energy will be used to charge this battery unit. Still, there is additional extra energy. If that energy is left there, the temperature or this voltage will be increasing. That is a problem. So that energy will go like this, and this is the shunt regulator. It's kind of converter, but it just consumes the energy. Right? This is installed on the surface of the satellite. That place is very cold. Okay, so this is very good heat sink. So they spend some energy here, extra energy here, and this load converter, and this one works as voltage regulator, and this voltage is regulated at 180 volt. Okay, with minimal ripple component, with minimal fluctuation, and now this satellite is orbiting around here. So it is somewhere here. So somewhere here, it goes into shade of the Earth or shadow of Earth. It's called, this is a sun-in mode. This is the eclipse mode. Okay. Then this switch will go like this. Then this sun is generating the same energy, but this satellite is receiving only 1/10 of the total energy, 10% like that. So there is some energy deficiency. Then this switch will go this port and put out some energy from the battery unit, and this battery will provide some additional energy to regulate this at this volt and to provide the required power. That is the basic structure of space power system. In there, this filter stage is located in every input port of every power converter for the reason I explained earlier. All right? And the managing power level and improving the dynamic of this bus. Suppose one additional load is attached, there is some disturbance. Disturbance should be minimized. Otherwise, something will be affected, and maybe this guy, there is some telescope, then telescope will transmit false image of something, okay? Then people will misunderstand there is just something in space which is just coming from the fluctuation of this voltage level, okay? They should be avoided. Okay? So there are a lot of research. There was, and there is, and there will be a lot of research area in this spacecraft power system. Okay, so eventually maybe we will have a chance to discuss the dynamics and control of this power system. I was involved with this business long time in the state. Okay, so